Welcome to the next talk in series 3 of our EDT community seminar series. It's good to see you all here. Today we have a great talk lined up, but I'm just going to quickly show you the schedule for the next talks so that you're all up to date. So if my slides move along, there we go. So today we have Mark Harman with us, and I'll intro his talk in a minute. In a couple of weeks, we then have Marcelino Rodriguez Cancio to give a talk on Le Twin C'est Chic, digital twins for fashion application. And then following that pattern of every 2 weeks, we are finishing with a panel discussion. And if you haven't attended one of our panel discussions from series 1 or series 2, you really should give it a look. We've had some great discussions during these panels and they're definitely worth attending. Now on to today's talk from Mark Harman. So Mark is a software engineer at Meta. And he's going to give a talk on Facebook's cyber digital twin called WW, which is designed to tackle challenging technical problems in software safety and privacy for platforms such as Facebook and Instagram. Mark Harman is a software engineer in the testing and verification team at Meta and part-time professor at UCL. He's previously won the ACM Outstanding Research Award in 2019 and a fellowship of the Royal Academy of Engineering in 2020. We're very excited to have you here, Mark. I'll hand over to you.
Thanks very much. Thanks, Thomas, and thanks, Daniel, and others for the kind invitation. So in today's talk, I'm going to be covering what you might think of as a digital twin that we've been building and using for testing it itself at Facebook. I'm just going to share my screen. So hopefully now you can see my slides. So yeah, I want to mention that everything I say today is my own opinion, not necessarily those of the company Meta that I work for. That's the company that owns Facebook, Instagram, WhatsApp, and other products like that. But it is joint work with all of these people I list here on this slide. And although it's my opinions, not theirs, I've definitely been inspired and influenced in everything I say by working with these wonderful engineers, managers, directors, and thought leaders. So without any further ado, I shall mention that everything we talk about in today's talk is covered in some research papers. So I'm essentially going to be trying to encourage you to have a look at some of these papers that describe what we're doing in the company. And probably the go-to paper, like if you just want to look at just one paper, would be this one, Facebook's cyber digital twins. So I'm going to be giving a little bit of context about who I am and where I come from, how I got interested in this area. And I'll tell you about our Dub simulation platform at Facebook. And argue about why this is a digital twin, and in particular, a special kind of digital twin, which we call a cyber digital twin, to be contrasted with cyber physical digital twins. And then I'll tell you about how we test those, and hopefully there'll be plenty of time for questions at the end. So my background, I actually only ever had 2 companies in my life. The rest of my life, I was an academic, one when I was 15 and one when I was 50. And in between, I was an academic. So the first company I ever worked for had as a startup, if you will, I suppose we didn't call it startup in those days, was called Firefly Software. I was 15 and I had this game, a sword fighting game for a Sinclair Spectrum. Anyone who's of a certain age may remember these computers. They were among the first home computers. And the interesting thing is, it was actually a game, but curiously enough, the marketing department of the company that bought the game and the company marketed it as a simulation on the dust jacket for the game, which I thought was interesting. You can see that actually it really, to say it's a simulation is kind of a stretch. This is the game itself, and you played it on a conventional television set in those days. And this is the game. Calling it a simulation is probably a marketing ploy rather than a technical description. But one thing that's interesting that I want to mention, because it has an interesting resonance later, is that I later found in a survey of software games that this was the first game ever to offer the ability to capture and replay a game that you'd played. So you could write your game out to cassette tape and then replay it in later to see it. That was option 2 there. So Fast forward about 30 years, and my second startup was Magica with two great colleagues at UCL. And we were acquired by Facebook, and we built this testing technology. And then we were presented with this enormous problem of tackling software engineering at scale. So 2.91 billion people per day use the products. It's probably some of the most used software products in the history of computing. And what this means is that the number of commits that are landing is one every few minutes. I mean, it's over 100K commits to the repository per week. So we deployed this testing technology called Sapiens, which essentially uses computational search to try and find test cases to reveal what we would call the implicit oracle. So things that we know implicitly should not happen on the app. So it shouldn't crash, it shouldn't go out of memory, it shouldn't fail to respond. And this is what it looks like when we're running the app. This was the initial deployment into a cloud of emulators for Android apps and iOS, in fact, here. And what you're really seeing here is a kind of a simulation, in the sense that each time one of these emulators gets sparked up, it simulates what a user can do by simply pressing lots of gestures on the surface of the device. So in some sense, it's simulating users, although it's very much like a kind of a simulation of random kind of behavior. And the other thing that was interesting is we tried very hard to stop these individual test user accounts from communicating with each other, because that would have made the tests flaky. But that led to, and we published a paper about this if you're interested, on the deployment of Sapiens at Facebook. But it led to several other interesting developments. One is that I just want to briefly mention is SapFix, which was, as well as testing to find these bugs using the simulated user behaviors, we also tried to automatically fix some of those. And this was work done by a PhD intern at the time, Alexandru Marginian, who then went on to become an employee at the company. And this I wanted to mention just because it illustrates just how much impact you can have as a PhD student by doing an internship in a company like Meta Platforms. So Alex did his internship, and as a result, he's able to say, to people who he might meet, well, put your hand up if you use any of these apps, Messenger, Facebook, Instagram. If you are, you're running software that's been automatically fixed by code that I've deployed into the company as part of my PhD research program. So he's directly impacted over 2.9 billion people with his research through that internship program. So as I mentioned, we tried hard to stop these simulated user journeys through the apps from communicating with each other, because to scale it up, we'd have to run hundreds of these at any given time. And if they started communicating with each other, each would behave slightly differently, which would make the test flaky. But that gave us some ideas that, well, maybe we could exploit that kind of behavior to build a simulation of the user community itself. So use these test users as a community that essentially simulates the behavior of a whole community on the platform, but don't simulate the platform itself. So we take the Facebook infrastructure of devices, processing elements, and data stores, essentially. We take that existing infrastructure, and on it, we deploy bots whose actions and observations go through the real infrastructure. So when one bot messages another, it uses exactly the same stack of code that you and I would use when we message each other. And then we can reward the bots for behaviors that we would rather not see on the platform, and therefore use that as a way of testing that those behaviors do get caught, and even potentially enhancing the products to make it harder to achieve that. Of course, all these interactions are between bots only. So the dub bots interact with each other. We call it dub, by the way, WW, or dub for short, because it's a kind of cut down version of the overall dub infrastructure. And we described this in a paper from 2020 about what we call web-enabled simulation. So the idea here is that, unlike a traditional simulation where you might have to simulate the whole of physics or the part of physics you're interested in to simulate a physical artifact, here we're simulating only the user behavior, but the engineering artifact is itself software. So we can execute on the real software itself, and that has some profound consequences. So the kinds of things that we can do with this are we can go after harmful behavior, so things like scamming and spamming. And in particular, we can try and favor prevention over detection. So I like to illustrate this distinction with an example, for an analogy from driving. So if you're driving along a road in a camper van, having a nice time, and suddenly you get nearly knocked off the road because somebody shoots past you, they're speeding way past the speeding limit. The problem is there's not a lot you can do as the driver of the camper van, but as the provider of the platform, the road designer, you can use various mechanisms to try and overcome this behavior. So the bad behavior in the analogy is speeding. The platform is the road. What can you do? Well, you could deploy cameras. So in the UK, we paint these cameras orange or yellow so they can be distinguished. It's a detection technology. We don't stop people speeding. We just capture an image of them when they do. And then there's prevention, where we would essentially put speed bumps in the road. Now, in a physical situation, neither of these is ideal. The prevention technology doesn't actually prevent the behavior, and even normal users who aren't exhibiting that speeding behavior will still get damage to their car as a result of the behavior. But if we transplant that into the software world, we use that same approach. We want to try and design mechanisms like those speed humps that will tend to prevent the harmful behavior, but not the normal behavior. Then what we do is take the actions and observations that the bots are performing on the real infrastructure, and we impose software equivalents of speed humps. So what I mean here is things like rate limits that will limit the way in which the bots can perform those actions and the degree to which they can make observations from them. So let's make that specific. Imagine we have a constraint vector that says that this bot here can only send 4 messages a minute, and it can only read 12 messages a minute. And maybe there's some other limit, 17, that's affecting the content of the messages and sizes. And then the other bots have different values for these same constraints, and they might mix and match them. Then what we've got in this constraint vector is essentially a search space. It's, of course, a much larger search space than that, because there are so many ways in which we can tweak the ways in which actions and observations can occur. And in so doing, what we're doing is we're simulating the effect of possible either new policies or new features that we can install into that infrastructure that would tend to have the same effect as those rate limits that we've simulated at this mechanism layer. So the interesting thing here is we're simulating the user's behavior at the top there with the bot's behavior. We're simulating possible features that we might add to the infrastructure, but we're not simulating the infrastructure itself. So we get a very realistic but very scalable simulation of what might happen in a counterfactual world where we might do new possible things. And we can treat that mechanism layer as a search space. And what we're really searching for is an ideal sweet spot where it's much harder to do the harmful things, but it's not harmful to do the normal things. So in the driving analogy, the speed humps, they don't really work that well because they don't stop people from speeding, and they harm people who are actually driving normally. They harm the cars, at least. In the software world, we hope and believe that we can find features that we can add to the infrastructure that will make it simultaneously harder to achieve harmful behavior, say, for example, crawling with the intent of scamming another innocent user, while at the same time not making it harder for someone to do normal behavior, like going around the social graph trying to meet new friends. And the way we do this technically is we can think of this as a search space in which you might say, well, you're looking for a needle in a haystack to find that sweet spot. But that's exactly what an area of software engineering known as search-based software engineering is all about. It's all about essentially formulating hard multi-objective optimization problems, possibly in constrained spaces, possibly also noisy spaces where the fitness function is either not always accurate and is not always complete. But nonetheless, you get enough signal in that fitness function that you can guide a computational search to find reasonable solutions. They may not be optimal. In fact, it's an NP hard problem, but they will be better than your current offering. That's the hope. So we actually had a funding call last year for this, where we engaged with the scientific community. And I just wanted to mention that in the context of this talk, because I know that some of the audience are academics, and if you're interested in engaging with us on this as a research agenda, we'd be very much interested in talking about opportunities for collaboration. So what about digital twins? Well, let's first of all just do a quick handshake on what is a digital twin. There are many, many different definitions in the literature. I think it's important to distinguish a simulation from a digital twin. So suppose we are simulating the behavior of a vehicle, of a car. So we have the physical device, the car itself, that's a physical engineering artifact. And then we have above it the simulation of that same vehicle in software. Now, ideally in any simulation, the simulation is informed by reality. So observations from that real engineering artifact will inform the simulation, and the simulation will, in the due course, inform the design of the next version of the car. So we can imagine that those two arrows are largely, in traditional simulation, governed by humans. Humans will extract from the engineering artifact a whole bunch of physical properties to model. That becomes the simulation. They'll run the simulation, and maybe over a period of months or even possibly years, they'll form conclusions from their research and their experiments in the simulation, and those will inform the next generation of the product or the next release. But what if we automatically perform both of those arrows? So we automatically extract information from the physical artifact, and that informs the simulation. And the simulation then automatically gives feedback to the physical device, so that the physical device behavior changes in real time in response to the simulation response. This is when we get what is called a digital twin, in my opinion. This would be my definition of digital twin. I know it's not the only one, but it's the one that I'd like to use in this talk. So an important observation to make at this point is that if we're talking about a car or a chemical engineering plant or an oil rig as the engineering artifact, then what we have is a cyber physical digital twin. So the cyber part at the top is simulating the physical part at the bottom. There can be this real-time feedback loop, which makes it a digital twin, but it is nonetheless a cyber physical digital twin. But what if, oh, and of course we can deploy that cyber physical digital into the car itself, and then it can be responding in real time. That's great, but it is cyber physical. That's the important point. Now, if we think about this dub platform that we've built, it is a simulation, but it's a simulation, and taken in its entirety with the use of the bots and the mechanism layer and so on. It's a simulation of the real engineering artifact, but the real engineering artifact in this case is itself also a digital artifact. So as software engineers, we're in this amazing, unique world in that our engineering material is unlike any other engineering material that any other engineer has ever encountered in the history of engineering. And in our case of digital twins, it makes a really profound difference. So instead of it being a cyber physical digital twin, what we have is a cyber digital twin. Now, you might think that's just playing with words, but think about the technical consequences of that observation. Instead of just saying that the engineering artifact is modeled inside the cyber world, it's the cyber artifact that's modeled inside the cyber world. So we could have a cyber digital twin of a cyber digital twin. What we essentially get is a nested hierarchy of simulations, each of which can take signals from the thing it's simulating and give back responses in real time. So as soon as you move to a cyber digital twin world, you for free get the potential to have a hierarchy of digital twins where the base case is a physical world and the cyber world built on top of it each simulate each other. You might say, well, what's the point of that? Well, we found this to be a tremendously powerful framework for doing simulation and digital twins at Meta. So if we think of the real Facebook platform as a cyber physical digital twin itself, it's a model of social interactions in the real world. And on top of that, we build a digital twin by having a simulation, and the simulation is online. The bots are simulated, but the online simulation is on the real platform. We can then build a further abstraction of that, which is an offline version, or a synthetic model of the behavior. So now we are simulating the online simulation itself. And further still, we experimented with the idea of, well, we could even build an emulator that tries to predict what our offline simulation of the online simulation of the real platform would do. You think, why would you build this hierarchy? Well, the important thing is, as you go up the hierarchy, the computational time to produce a simulation decreases exponentially. Of course, the faithfulness to the likely behavior on the real platform also decreases, but not exponentially at least. So you get an engineering trade-off, that classical engineering trade-off in computer science between precision and speed. As we go up the abstraction hierarchy, we get the ability to much, much quicker get signal from our simulation. And if we can then balance that against the consequent loss in fidelity to the real platform, such that our simulation results are computed much faster, but are sufficiently realistic to be useful as predictors or as intervention in deciding what new features to deploy, then we have a huge engineering win. Because as you can imagine, simulating a whole user community is potentially computationally expensive. And we found that in early experiments that the emulator approach was several orders of magnitude faster. So at each stage, we have these cyber simulations of the next layer down in the platform. This is only possible because we have a cyber digital twin. And you can think of the base case, if you like, to this recursion as being the cyber physical digital twin. I think this observation, this idea of cyber digital twins and this ability to build a hierarchy is a very profound idea that could have consequences in other aspects of digital twin research. But we've used it very much in our company to balance this precision speed trade-off. And there's a paper about this, as I mentioned. So when we build the platform, we need to ensure that we have a number of features that make it useful as a platform. I just want to spend 5 minutes telling you a little bit about those. So three features in particular that we've built into this platform are the ability to plug and play, flexibility, and scalability. To make any research ideas work in practice in industry, scalability is really important. The other two are also very important for usability, as you can imagine. So plug and play, what this means is that we can do multiple different things with our platform. So for example, we can replay things that we've seen in practice so that we can check, for example, the behaviors that shouldn't happen won't happen again. And we can also build policies that build virtual worlds with our cyber physical digital twin. So let's look at these two. So replay essentially means, like in the real world, on the left-hand side, we might see that, in the real world, very specific things happen. So for example, when people start streaming videos and then people react to them in real time. And in the virtual world, we want to abstract enough of that so we can keep the realistic real world behavior. So, and sometimes that might mean not just keeping things happening in the same order, but also actually replicating the time intervals between these things from happening. So we have the ability in our world to replay things, which is, although it's a relatively technically, conceptually simple idea, it's an incredibly powerful one, because of course you can replay them then in worlds which you've permuted certain details, and now you're replaying what has happened in the past, but in a counterfactual possible future. The other thing we can do is we can build communities of users with different personas. So for example, if we have a set of users here, of course, the real graph is much, much bigger, but imagine we have a graph of users with friendship connections. And here we're seeing their age, their gender, and their country of origin. So we can simulate communities, capture individual properties that make them different as different models of different kinds of persona of people, and give them a rich texture of background, so things that they've liked, groups that they're in. So essentially you're modeling a whole community here with a community policy. So we have this plug and play ability that allows us to do multiple different things with the platform. It's also a very flexible platform. So we need to be able to model not just the Facebook app, but also Instagram and WhatsApp and other potential products and services that might be deployed by the company. And we do this by having a simple overall structure for our simulation. The details are in our papers, but in particular, there's an environment component that you can see here, the third along, where we can substitute one environment for another: Facebook, Instagram, WhatsApp, other environments, and so on. Finally, it has to be scalable. So this environment that we use is also something where we can actually scale up the number of bots that are running on that environment, running them concurrently, as you can imagine. So how does one go about using simulation to test and testing that the simulations themselves are correct? There's two challenges here when you face the problem of software testing applied to simulation. And one of the key problems you face is that you're inherently modeling something that is stochastic. That's what simulation is all about. And also in our case, if you're modeling on the real social graph, so if you're running bots over a real social graph, or any kind of model of it which is capturing the temporal behaviors, then the graph changes over time itself. You know, links get added, new people join, and so on. So these two problems make it hard for testing, because when you run a test 1 minute, you might get a different answer to the next. And we found that metamorphic testing is very valuable here. So the idea of metamorphic testing is usually illustrated with this simple example. Suppose I'm trying to test the ability of a piece of software to implement the sign function. So very simple mathematical function. This is just an illustrative example. But suppose we don't actually know what the specific value at this level of precision should be for sign. Okay. But a metamorphic relation is that whatever the value of sine x is, it ought to be the same as sine 2 pi plus x. So we take this property of the thing we're building, and we essentially test that property, and that allows us to test this metamorphic relation without necessarily having a complete specification of what the overall behavior should be. Now, metamorphic testing is a widely studied area of research. It's been studied for, I think, nearly a quarter of a century now. The first papers were at least 20 years ago. And the deployment at Meta on Facebook platforms is the first case in which metamorphic testing has been deployed into continuous integration in industry, and it was covered in a paper. I should mention that around the same time, Google also deployed metamorphic testing, not into continuous integration, but in a model, essentially testing third-party graphics libraries. So what we're seeing is that this area of research that's been researched for some 2 decades now is starting to find its way in industry. The deployment we have was the first time it's been in continuous integration, but there have been other companies that have deployed metamorphic testing. If you're interested in the details, that there is this paper which was published at ICSI last year in the SEIP track, so testing webination. I want to give you some highlights from the paper to illustrate why this is a way we can test simulations, and I think that some of the ideas would translate to other simulations as well, and therefore to digital twins. So suppose we have a bot that's doing a traversal on a social graph. Here's a model social graph, obviously much more than the real one. So the bot might start off by traversing produce state 1, then state 2, state 3. Each one of these is visiting a node in the graph, essentially visiting a user account, a profile. Now, if we take the same input to a bot and we started in the same state and we run that bot on the online simulation, then we won't get the same behaviors. Very quickly, they'll diverge. And that's precisely because of this stochastic nature and churn. So tests essentially are flaky. In the language of software testing, we say our tests are flaky. And that's because in the real world, there are state changes happening all the time, independent of the test we're running. And the infrastructure itself is non-deterministic. So inherently, in order to build an infrastructure at this scale, hundreds of millions of lines of code, the responses from, for example, machine learning classifiers and from various pieces of infrastructure that provide guidance to the overall behavior of the platform, they are inherently non-deterministic, where that non-determinism shouldn't actually affect the end user experience. So this is to get speed out of the overall platform and make sure that it's responsive, for example. However, from a testing point of view, that means we get flaky tests. So the graph itself could change. So, for example, as the bot does that traversal, it could be, oh, now suddenly that user there is no longer a friend of the other user. So, excuse me. So I was going to go from 2 to 3, but as I went from 1 to 2, 3 no longer is a friend of 2. You know, this is what happens in the real graph. So now the behavior will be different because the social graph has changed. In the offline mode, it's very unlikely that will happen, because the offline mode allows us to essentially capture the whole graph and then run it in an offline mode. So in offline mode, if I start in the same initial state and I give the same input to the 2 bots, then they should produce the same trajectory. So this allows us to think of ways in which now we're in an offline mode where we can control at least that churn, that we know that the global variable on which we're executing will stay constant. We can now think about what would it mean to make metamorphic relations that will allow us to test behavior without knowing the true behavior. So that is, we don't know what the bot should traverse in this graph. We have no idea, right? I mean, otherwise we wouldn't need a simulation. That's the kind, we're using the simulation to understand what kind of behavior the bot might engage in. But suppose we bring in this idea of rate limits, these speed humps that we were talking about. So in this case, suppose we say, you know what? We're only going to allow you to see a very restricted number of connections on the graph. So as the bot's moving around the graph, maybe we'd say, well, you don't see all of those connections. Now you're constrained to go to this step next, and so on. So as we tighten the rate limit, the behavior of the bot in this graph must be inherently reduced. How do we exploit that to make a metamorphic relation? Well, suppose I take one of these harmful bots, one that maybe is trying to find people to scam on the social graph, that's the red one at the top. And then I take a harmless bot, one that we don't want to be hurt at all in terms of their experience. They're trying to find friends. We start both bots in the same initial state, but we rate limit them. So we say you can only see at most one connection in the graph. And then we run them in the offline mode. So the graph itself isn't changing underneath their feet. The rate limit means that they can only see at most one connection. But the two bots are actually trained using entirely different machine learning algorithms, because one's trying to emulate harmful behavior and the other harmless. They couldn't be more different in that sense. But in this very constrained world, they must behave the same, because they can only see at most one connection, and therefore they must perform the same trajectory. So this gives us a nice way to use metamorphic testing to test the behavior of a simulation when we don't know what the outcome of the simulation should be. And we can't know what the outcome of the simulation should be, because otherwise we wouldn't need a simulation. So it's very necessary to find techniques like this that allow us to still produce meaningful tests, but without actually knowing what the trajectory itself should be. So what we're doing here is we say, I don't know what the trajectory will be, but the harmful bot should do the same trajectory as the harmless bot. And you'd be surprised how this approach can shake out all sorts of interesting bugs. We give examples of a few in the paper. They often tend to be kind of corner cases, which are often missed by other tests. So another example is we can use the relationship between different bot personas and get what's known as a statistical metamorphic test. So suppose I have two bots now. Neither of these is harmful or harmless. They're just bots simulating, normal kind of user behaviors. So I suppose harmless, I should say. But we're not trying to model any particular behavior, but we are modeling a particular persona. So the bot at the top bot is modeling someone who's in their 20s, and the bot below that is modeling someone who's in their 50s. And now we can model these on the online graph. So they could actually be on a graph that's changing under their feet and so on. So interestingly, this is robust, even in the presence of some of these churn type behaviors we talked about. The thing is, whatever trajectory the upper bot does, we can collect the average age of profiles it visits. Let's call that A1. And we can do the same for the other bot. Now, because of a property called social homophilia, I think I've pronounced that right. It's the property that you tend to make friends with people who are alike. They would have a similar persona to you. So it's a statistical property. We can't predict exactly who you'll be friends with, but over a period of time, if you do a walk through the graph, the persona 20s bot will tend to visit younger people than the persona 50s bot because of this homophilic property. So what we'd expect is that if we run our simulation for long enough and we have a long enough trajectory, then the expected average age of the persona 20 bot will be lower than that of the persona 50s bot. The interesting thing here is, here we have a statistical test using a metamorphic relation that is robust even in the presence of all sorts of non-deterministic behaviors. So we don't know what the bots are going to do. We don't know what they're going to visit. We can run them in the online mode. They may do different things every time we run them, but overall this statistical property should still hold. So it gives us a way to catch bugs without really knowing what the software is going to do in any particular case, and even where it might do slightly different things in each case, which is, from a testing perspective, that's quite something to be able to do. Excuse me. So we've implemented these approaches. We talk about them in the paper, and it's an approach to metamorphic testing. We also were able to implement end-to-end testing using the same framework. And we showed that regression testing is just a special case of this metamorphic testing. So that gave us sort of three features for one development effort. So in summary then, in today's talk, I've talked about a very brief summary of my journey through industry and academia, focusing on the two bookends, which have been startups and industrial experience. What we're doing in the company is a kind of digital twin, but as I say, a cyber digital twin. I've shown you the dub simulation platform, and in particular how the cyber nature of the platform allows us to have this recursive set of digital twins, each built on top of the other. And I've talked a little bit about how we use metamorphic testing. We talk more about this in the paper. It's a system called MEA. MEA stands for Metamorphic Interaction Automaton. It's the testing system we build partly to test the simulation itself, the dub platform, and partly we also use the framework to make tests that test behavior of other systems in the company. So for example, classification systems to check that they are correctly classifying harmful behaviors. I talked a lot about papers that contain some of the information that I've talked about in more detail. It may be a bit overwhelming to have all of those papers presented. So if you really just only have time to read one paper and you want a kind of starting off paper on the work we're doing, then I would recommend this one, Facebook's Cyber and Cyber Physical Digital Twins, which I think if you just Google that, there's a publicly available version. So thank you very much. I hope I've left plenty of time for questions and discussion.
Yeah, great. Thank you so much, Mark. That was a really great talk. I'll give you a virtual round of applause there. Yeah, so